In kinetics, the rate law explains what happens. The rate of the reaction is described in a mathematical equation that's related to the concentrations of the reacting species, the orders of the reaction, which are determined experimentally, and the rate constant, which is constant as long as you're at constant temperature. But we haven't talked about why does that govern the kinetics of the experiment. Recall we talked about the factors that we know affect the rate of the reaction way at the beginning of this series. Increasing the concentration increases the rate of the reaction, increasing the temperature increases the rate of the reaction. We have these known things about what happens. What we want to talk about here is the theory behind why that happens. And the theory behind why that happens is known as the collision theory. The collision theory has several points. Sometimes they're summarized a little bit differently depending on where you get them, but essentially what the collision theory says is that in order for a reaction to happen, the reacting molecules must collide. In order for A and B to form products, A and B have to hit each other. They have to run into each other. If they're all the way across the room from each other, no reaction is going to take place. It may seem kind of common sense to you, but again, we're talking about why this happens. Another thing, in order for molecules or particles to react, they must collide with sufficient energy in order to react. So there must be a sufficient energy for the reaction to take place. Now you may be thinking, well, wait a minute, some reactions are exothermic. That means they release energy as the reaction proceeds. If a reaction releases energy, why does it take energy in the first place? And the reason why it takes energy in the first place is because in order for the molecules to rearrange themselves to form products, you have to break bonds. You have to break some bonds from the reacting molecules, and you may recall from a previous chapter that it takes energy to break bonds. So even if ultimately you end up with a release in energy, you need an input of energy for that reaction to take place in order to get the bonds broken of the molecules so that the products can be formed. This sufficient energy is called an activation energy. The abbreviation for activation energy is usually E sub A for activation energy. And the third requirement, or the third reason why we see what we see when we look at the kinetics rate laws, is that the molecules, not only must they collide, not only must they have sufficient energy, but they must be oriented properly. You may recall from previous chapters that not all molecules are spherically symmetric. Not all molecules are symmetric in all three dimensions. Molecules have sides. One side might have a chlorine, the other side might have an oxygen. Well, if the products require the chlorine side of the molecule coming in contact with the other reactant, then the molecule has to be turned such that the chlorine molecule does come in contact with the molecule it needs to react with. So the orientation of the molecules must be correct. All right, these three essentially prove, well, not prove, we can't prove a theory, but they explain why we see the kinetics rate laws that we do. These are explanations for why we see what we see. So let's talk about how this explains why we see what we see. You may recall from your exposure to thermodynamics already, talking about the energy of reactions, that some reactions are exothermic. And if we look at an exothermic reaction, for example, that means the reactants start at a higher energy and the products end up at a lower energy. So let me draw an energy diagram. It's a graph of energy. In our previous exposure to thermodynamics, we could draw this, and we would simply draw my reactants up here, my products down here, and we'd say, aha, it goes down in energy, therefore it's exothermic. But it's a little more complicated than that. So what we're going to look at here is a timeline that goes along with it. My reactants start up here, and my products end up down here. That's why it's exothermic. But what happens in the meantime? Well, in the meantime, The molecules must collide, they must have a sufficient energy in order for that reaction to take place, and they must be oriented properly. And so we can explain that on our energy diagram as first, the reactants must go uphill, they must go to a higher energy in order for the reaction to take place, and then the energy drops. This amount of energy that they have to go up is called the activation energy. This is my E sub A. This amount of energy is the amount of energy required to get over this path. This is a path to the products. Here at the peak of the path, here at the top portion, we call this a transition state. We also can refer to it as the activated complex is there at the peak. This is the orientation of the molecules, the reacting species, as bonds are breaking and bonds are forming in order to go on and form the products. And so my path is not just a direct reactants going to products tumbling downhill, but the molecules have to get over this energy barrier, and that's the activation energy. If we look at an endothermic reaction, we see a similar path. This is my energy diagram. My reactants, however, are going to start at lower energy. My products are going to end up at a higher energy, but my path is not simply from here to here. I actually have to go over a similar energy barrier. And the energy barrier that I have to go over is the activation energy. So my activation energy is always defined as the energy between my reactants and that transition state, that peak in the energy curve. So in this case, my activation energy is this distance. All right, and I could calculate it if I had my axes labeled, if I had actually graph paper and numbers on them. And so these are what my energy diagrams look like. They show that this energy barrier has to be overcome. If we look closely at the transition state, we see taken into account orientations of molecules, and again, the fact that the molecules must collide in order to go on and form products. What we want to do next is we want to talk a little bit more about this temperature effect. The collision theory actually does help us to explain why we see what we see when we change the temperature. What we talked about early on in this chapter is that if you raise the temperature on a reaction, in general it goes faster. So you raise the rate or it goes faster. Temperature is proportional to kinetic energy. The higher the temperature, the more kinetic energy the particles have, the faster they move. So as you raise the temperature, the particles move faster, they're going to collide more frequently, they're going to collide with more energy, and therefore you will have a faster production of those products because you're meeting the requirements for the reaction to take place. And so we do see how the temperature plays into looking at why do reactions happen the way they do. It makes sense that raising the temperature then would raise the rate of the reaction and make it go faster. There was a man, his name is Arrhenius. Arrhenius was a guy who was looking at this idea of the rates of the reaction versus the temperature, and he came up with an experimentally determined equation which relates the reaction rate to the temperature. This is known as the Arrhenius equation, and the Arrhenius equation looks like this. All right, let's talk about what these are. This is my rate constant. We saw it in our rate law. It is a constant numerical value as long as you have a constant temperature. That is it's the proportionality constant for the rate law. A is often referred to as a frequency factor. It is a numerical value that is related to the number of collisions, the frequency of the collisions that result in the production of the products. It's a little vague and fuzzy. We don't do a whole lot with it in the general chemistry class. If you go on and you take physical chemistry as a junior or a senior, you'll spend some time talking about kinetics in a lot more detail, and you'll do a lot more with this value. But for us, we don't do a whole lot with it. E sub A is our activation energy. We do worry about this in this semester. Our activation energy is again that energy required to get over the energy barrier. R is my ideal gas constant, but it is in units of energy, so it's the 8.314 joules per mole per Kelvin, not the ideal gas constant that we use in PV equals nRT. It's the one that has units of energy. Often we'll see the activation energies in kilojoules instead of joules, so you might use your R in kilojoules, 8.314 times 10 to the minus 3 kilojoules per mole per Kelvin. Just a matter of your units. You do have to watch your units. And T is our temperature in Kelvin. And we can see from this equation then, if the T gets higher and higher and higher at higher temperatures, first of all, let me stress this. My activation energy, we saw on the energy diagram in the previous screen, this is constant for a particular reaction. It does not change as you change the temperature. It is a constant numerical value associated with how much energy it takes for the reaction to proceed and get over that energy barrier. It is always constant. The rate constant is only constant at constant temperature. If you change the temperature of a reaction, the rate constant changes because the proportionality constant for the rate law changes. But activation energy does not change as you change the temperature. It's always constant for a particular reaction. If I raise the temperature, that's here in the denominator of the exponent, this is an inverse log with a negative sign on it, and if you kind of follow through on that math, as the temperature gets higher and higher and higher, the rate constant will get larger and larger and larger. Again, you kind of have to follow through the math on that or plug in a couple values to prove it to yourself. But larger numerical values for temperature, everything else staying constant. My frequency factor here, the A, is constant. My activation energy is constant. My R value is constant. K will get larger. So the reaction will go faster at higher temperatures because the rate constant is larger. Now, this form of the Arrhenius equation isn't that useful to us at this point, so I want to do a little algebra on it and get it in a more useful form. All right, if I take the natural log of both sides, I end up with the log of K is equal to the log of A minus E sub A over RT. I hope you've had a chance to practice a little bit with natural logs. Do a little bit more rearranging, one more algebra step. I have the log of K equals minus E sub A over RT plus the natural log of A. This is the equation for a line, y equals mx plus b. On the y-axis, I would plot the natural log of the rate constant. On the x-axis, I would plot 1 over T, and that temperature, remember, has to be in Kelvin. And what I will find is a straight line. It is a negatively sloping line, and the slope is equal to negative E sub A over R. So this is a way that I can find my activation energy, again, which is a constant numerical value for a particular reaction. I might run the reaction at several temperatures, determine the rate constant at each of those temperatures, make a plot of the natural log of K versus 1 over T. The slope of the straight line would give me my activation energy. If you only have 2 points is all you need to make a straight line. There is a format of this equation, a formula that's related to this equation, which is often used as a shortcut if there are only 2 points, and it looks like this. Let me caution you, the algebra on this equation is a little tricky. You really have to keep track of your 2's and 1's for your T's and your K's, and you have to keep track of your signs. One good thing to keep in mind as you solve, usually you're solving for activation energy but not always, is that your activation energy is always a positive numerical value. If you ever end up with a negative activation energy for this equation, you've done something wrong. So activation energies are always positive numerical values.